Hello, my name is Derek Rosendahl, and I am a postdoctoral research scientist with the South Central Climate Science Center. Today I will be discussing how to properly interpret global climate model output, and I will provide a few example figures of major results. Future climate projections from global climate models, or GCMs, are some of the most requested climate products by decision makers who are planning for the impacts of climate change. Global climate model projections combined with GCM historical output can be used to compare today's climate with what we might experience 50 or 100 years from now as a region, nation, or world. Even with the vast opportunities for using GCM output, there are significant challenges in using these products correctly. So I want to discuss the most common mistake that users can make and then show you some of the important results from global climate model projections. First, I know that most of us have used weather forecasts regularly, sometimes every day. Although the basis for climate modeling is similar to that of weather forecast modeling, the output from these different model types cannot be interpreted in the same way. Weather forecast models are started or initiated with current weather data measured by lots of different types of sensors around the world. So a weather model has an initial state based on specific conditions. From that initial state, the model steps ahead in time and makes a forecast for the next several days. This weather forecast depends on its initial conditions. This is why weather forecasting is commonly called an initial value problem. It relies on good observations of the weather at the time the model starts its forecast. The global climate models used for climate change decision-making are not initiated with actual observations. They also are not nudged to be close to actual observations. Instead, GCMs are driven by conditions that bound the model. These boundary conditions allow the models to develop major climate features like polar and tropical air masses, mid-latitude low-pressure systems, tropical cyclones, subtropical high-pressure systems, Arctic sea ice, rain shadows on the leeward side of mountain ranges, and much more. But these boundary conditions are not like the observations of temperature, rainfall, and wind that are used to initiate weather forecasts. They are big-picture forcings on our atmosphere, like how much radiation arrives from the sun, where continents and mountain ranges are, and what the concentration of each gas in the atmosphere is. This is why climate projections are commonly called a boundary value problem. They only rely on the changes in the big picture forcings over years, decades, or centuries. So global climate models represent the decadal climate patterns across the world. They do not simulate specific weather events. This fact leads to one of the most common mistakes by users of GCMs. They think that the historical output of GCMs represent exactly what occurred on any given date. For example, they expect to see a large hurricane strike New Orleans on the date labeled August 29, 2005. But a climate model should not be expected to have a Hurricane Katrina on that date. It should have hurricanes that make landfall in Louisiana during hurricane season, but not to simulate a particular event. As a result, users should not try to assess the performance of a climate model by comparing its output directly to observations on a daily, monthly, or even annual basis. With that understanding, let's look at some output from a group of global climate models. Normally, we see this output as a map of a variable, like average temperature, for a specific time period, like 1980 to 2009. Or we might see a time series graph of how a variable changes over a long period of time, like from 1950 to 2010. In both of these cases, the boundary conditions of the historical period will be taken from the measurements of how these big picture drivers have changed in the past. We can't do that for the future period, so scientists have developed scenarios that represent what the future may be like if we continue emitting greenhouse gases as we have, or if we significantly reduce our greenhouse gas emissions, or some scenario in between. In the older climate model output, you may see these scenarios called A2 or B1, for example. Each of these scenarios speculate about what the future emissions may be. In the newer climate model output, you may see these scenarios called RCP 8.5 or RCP 2.6, for example. Each of these newer scenarios estimate how the radiative forcing on our atmosphere may change. Either way, you are able to examine a range of possible futures. Here's an example of how these different scenarios affect the global average temperature by 2100. We see that depending on our choices we make now on our emissions of greenhouse gases, our average surface temperature could be perhaps only 1.5 degrees Celsius warmer for our grandchildren, or a whopping 3.5 degrees Celsius warmer. We can also map these model results to see where these temperature changes are most drastic. In this way, we see that the Arctic is warming more than other places on Earth. We also find that the continents warm more than the oceans, especially in the high emissions scenario. And most importantly, the maps show us vividly that our surface temperatures will be much easier to adapt to if we can mitigate the rate of increase in greenhouse gases. These products are only a few of the many maps and time series that have been produced for decision makers. We don't have time to see them all now, but you can see many of them in the different videos of this series.